Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to introduce Ken Eguro, who is a PhD candidate in Department of Electrical Engineering at UW across the bridge. So he took the long trip over to talk to us today about his thesis work, and so he'll tell us about his take on reconfigurable computing and the challenges therefore. Ken?
Great. Thank you very much for the introduction. So today I'd like to talk to you a little bit about why I think reconfigurable computing is really just so compelling and some of the issues it has looking into the future. Now, personally, I think this is of particular interest because, as we'll see, the concerns that come up really end up cutting a wide swath through the field. So ranging from really kind of EE types of concerns. We're worried about transistor area or wire capacitance, resistance, that type of thing, all the way through to very computer science-y kind of problems of optimization algorithms and heuristics, right? So specifically, today I'm going to talk about just a few topics that kind of came up in my PhD research. So first, what are some of the architectural issues that existing FPGAs end up running into? And second, what are some of the problems that future applications pose to FPGA CAD tools? Now, so far, I've really kind of thrown out a lot of jargonish type of terms, so I'd like to begin with a bit of background. So first up, why do we even care about reconfigurable computing at all? Well, purely from a practical standpoint, okay, reconfigurable computing platforms are capable of producing extremely fast, extremely flexible implementations of a lot of really hard problems. Now, of course, classical problems like things like MPEG encoding, right, get a boost from using reconfigurable systems. But more importantly, it's really become an enabling technology for a lot of different fields. For example, okay, performing CT image reconstruction on a reconfigurable device is 10 to 30 times faster using a reconfigurable platform than on even the fastest CPUs. Now, in some sense, this kind of changes the landscape for a field like medicine, right? Not only are we reducing the cost and the complexity of potentially life-saving devices in this case, we're also increasing their accuracy too. In some other fields, we have really hard problems that all of a sudden with reconfigurable computing platforms become much more tractable. So from computational biology, we have like the Smith-Waterman, that's an algorithm to do DNA sequencing. Or protein folding. Astrophysics, military applications, network security, even things like finance get and see some of the benefits from this. So, for example, the Black-Scholes algorithm is something that predicts options pricing, right? And it's become hugely popular in no small part to reconfigurable computing platforms. So diving in. Okay, what exactly are reconfigurable computing platforms, and where do we get the benefits from? The performance benefits from? Well, basically, what we do is we use an FPGA or a whole bunch of FPGAs, and get most of the speed, power, and efficiency advantages of running on a custom piece of hardware. Now that said, we also maintain the kind of flexibility and just accessibility that we've really become accustomed to with software running on a general purpose processor. So first, what are they and why are they so much faster? Well, let's say that we have some application, okay, and one part of it is to just perform some large summation here. Okay. Now I can write a piece of C code that does this, and I can just compile it down to a conventional processor. Now, unfortunately, our CPU only has a limited number of computational units. So we're going to have to map all the operations that we would like to do in turn to the available ALUs. So first, we might perform these two additions and then these two, and eventually, okay, we're going to complete the summation. Now, of course, the standard CPU model is really what we've come to expect, and it's dominated our desktops for just decades because we can program the system to just do whatever we want it to. Now, that said, for certain types of computation, the standard CPU model is kind of wasteful. So as we all know, the control system for modern, multi-issue, out-of-order, superscalar, SMT, whatever processors is becoming more and more complex with every processor generation. Now, a huge amount of effort is devoted to simply, playing traffic cop or wedding planner, what have you, for a relatively small number of computational units. Now, this is one of the primary reasons why, if we really need high speed or low power devices, product engineers often turn to custom hardware or an ASIC. So in this case, if we want to produce, or if we want to perform a very specific summation, well, let's just build a chip dedicated to doing just that. So all we have to do is just, lay out the transistors for these 7 adders, and then wire them together exactly how we need them, and then we can fabricate this super efficient, super fast chip. Now that said, of course, ASICs do come at some cost. Right? So first we have to hire just a team of VLSI engineers in order to come out and lay all these things out. And second, we have to pay to have the chip manufactured. Well, this means that after like $1 million worth of investment and maybe a year worth of time, we can fabricate our first usable device. And of course, even after that, we better hope that this is what we really want to do, because we can't use this chip for anything else. Now, of course, for the vast majority of applications, this really isn't very practical. So this is where FPGAs come in. So FPGAs try to bridge the gap between ASICs and conventional processors. So they offer a lot of the performance and flexibility by providing a large array of relatively generic and programmable computational blocks that are embedded within a flexible and also programmable interconnect structure. So what the logic programmability allows us to do is, say, configure some of the logic blocks to be adders. And then after we've done this, we can link them together by programming the communication network in some appropriate manner. So in this way, we're still getting most of the advantages of building a custom piece of hardware. So that is, we don't have any of the overheads associated with a full-blown processor, and we can still put down as many computational units as we need, but we don't have this huge engineering cost of building a fully custom circuit. And we can avoid the engineering problems because, of course, we can just go to an FPGA company like Xilinx or Altera that goes through the trouble of engineering and fabricating one FPGA structure that they can sell to multiple different customers who each want to do totally different applications. Now, on top of this, most FPGAs also allow us to quickly program and reprogram the device over and over to do many different types of applications. And of course, these qualities are what opens up the huge opportunities for building all sorts of accelerators and coprocessors. So now that we've discussed what people like about FPGAs, let's talk about what people don't like. And that is their relatively low operating frequency. Now, although the adaptability and the flexibility of FPGAs is really what makes them such a great building platform, it's also this exact programmable nature that also makes them somewhat slower compared to other custom circuit technologies. Now that said, as an application developer, we can do something about this. Okay? So specifically, we can break our computation into smaller pieces using registers. So if we take the same adder tree that we had before, we can kind of insert registers between each of the different levels. So now, since we've decreased the amount of computation that we have to perform in a single clock cycle, instead of going through 3 adders, well, now we only have to go through 1. So basically, we can increase the clock rate of the circuit. Now, while we have to wait more clock cycles to get our final results, the general hope is that this is largely going to be offset by the increased throughput. Now, unfortunately, while pipelining can greatly help a lot of different applications, well, developers often have difficulty trying to map these heavily pipelined circuits onto commercial FPGAs. Now, largely, this is due to 2 different problems, and both are the focus of the research that I'm going to be talking about today. So first, conventional FPGA mapping tools are, let's say, largely ill-equipped, okay, to deal with heavily pipelined netlists. So basically, we need a large array of CAD tools in order to program an FPGA. Like a regular software compiler, the results that we get out the other end are only really as good as the tools themselves. Now, although I'll talk about the details of placement and routing in just a little bit, simply put, heavily pipelined applications really are fundamentally different than their non-pipelined counterparts. Now, what this means is that as customers demand faster and faster implementations of their circuits, the FPGA CAD tools suddenly have to deal with problems that they never really encountered before. Now, what further exacerbates this problem is the FPGA architectures themselves. Now, while, again, I'll talk about this in much more detail later on, essentially, the FPGAs that are commercially available today may not provide enough registering resources to efficiently implement heavily pipelined circuits. Now, what this means is that a lot of times we're not limited by the amount of computational resources on a device. We're limited by the number of registers on a device. So getting back to placement, let's just kind of look at some of the details. So as I had mentioned before, FPGAs are generally programmed with just a whole wide range of different computer-aided design tools. Now, of course, this isn't only due to just the sheer complexity of modern applications, but also because FPGAs offer a flexible but fixed amount of logic and communication resources. Now, the placement tool is really kind of the first line of defense that helps us make the best use of these limited resources. So what exactly is placement? Well, let's say that we've been given some application, right? And we've kind of broken it down into a net list of logic blocks. Okay? So during placement, we have to determine the physical location of each of these logic blocks. So exactly where in the array should we actually map these? Now, this process is, what makes this process difficult is that, of course, these logic blocks are linked in a very specific way. And of course, since there's only so many communication wires in our interconnect network, we kind of have to be a little bit careful so that we don't run out of communication capacity. So this means that ideally, our placement is going to reduce the amount of communication that's really needed to have in our system. So a good placement, like the one here, is generally going to try and shorten as many of the connections as we can. So the most popular algorithm for FPGA placement is a very powerful kind of a heuristic optimization technique, something called simulated annealing. So as the name suggests, the algorithm tries to parallel kind of the optimizations that nature makes when trying to form crystals in a cooling piece of metal. Okay, so basically, we start the system off. Ooh, I clicked through two. Okay. Basically, we start the system off with just an arbitrary initial placement. Right? So basically, we just take the logic blocks in the system and we just map them to any random locations. Now, at this point, we consider the kind of system temperature to be high. Right? This is very similar to, okay, we're just pulling a piece of iron straight out of the blast furnace or whatever. We then perturb the system over and over by randomly kind of moving the blocks around. Now, this kind of represents the random atomic movement that's present as our piece of iron begins to cool and some of the atoms start to crystallize. Now, basically, we always accept a good move. So that is a move that lowers the overall wire length required by the system. And we conditionally accept bad moves. So this ability to kind of make a move that actually makes the system worse, at least temporarily, actually ends up helping us overall during the optimization process. Now, this is because from wherever we start from, okay, if we only make moves that improve the system, we can really easily come to the point where we can't make the system any better because of some of the choices that we made earlier on. Now, so basically, by allowing the system to kind of get out of those ruts, or more technically, local minima, we can generally get much better final results. So basically, we gradually just kind of steer the system towards better and better placements by reducing the probability of accepting a bad move as the annealing temperature goes down and down and down. Anyways, eventually the system's going to freeze, and if we've done everything right, well, we're going to have a good placement. So basically, if we look at the cost of the system as the annealing progresses from a high temperature to a low temperature, we're kind of going to have a couple of wiggles here and there, but more or less, we're going to be improving the placement very, very slowly. Now, of course, taking a step back for a moment, okay, a small wire length isn't necessarily the only consideration that makes a placement good. Now, largely, this is because, of course, we have a fixed arrangement of logic blocks in an FPGA. So what this means is that all the logic blocks in our net list may not be able to actually be placed right next to all the other logic blocks that it's connected to. And what this means then is that oftentimes we have to make really a choice, right? Some of the wires might have to be longer than others. So what connections are kind of like the least important ones? So for example, in this application, right, A, B, C, and E are all along a longer logical path than D. Now, basically, if we make any of these connections kind of longer than absolutely necessary, we're probably going to be slowing the system down. So thus, if we're going to make any of the connections long, well, it's probably best to kind of make the ones that are connected to D the long ones. So existing FPGA placement tools, like the current de facto research standard, a tool called VPR, tries to take this into account by modifying the cost function that's used during simulated annealing. So we're trying to optimize not only for wire length, but also for circuit speed too, and this is something called timing-driven placement. So how this works is we incorporate a timing cost for every connection that changes, basically depending on how critical we think the connection is. So if we consider the criticality to range between 0 and 1, so 0 being the path that this connection is on is so fast that it doesn't really matter the timing at all, and 1.0 meaning the path that this connection is on is the slowest path in the entire system, and thus if we make this any slower, we're going to make the entire system slower. Okay? If we consider that to be the range for the criticality, we can see that basically this formula here makes delay on highly critical links really expensive. And conversely, delay is relatively cheap for nets that aren't so critical. Now, basically, in this way, we try to give special attention to timing-sensitive connections during placement. Now, while this is a really good theory, okay, one monkey wrench that kind of gets thrown into the system involves how accurately we can actually estimate the criticality of any given net as the placement progresses and we move all the blocks around. So, before we can really discuss that, maybe we should discuss how we actually determine criticality at all. So to determine the criticality for any given placement, basically we have to perform a procedure called static timing analysis. So static timing analysis uses delay estimates from our placement and kind of steps through the netlist from the inputs to the outputs, trying to determine the critical path through the system. So basically, we could go through here and say, well, OK, 2 plus 7 plus 1, we can get this output in 10 units of delay. And 2 plus 1 plus 1, OK, we can get the output in 5 units of delay. This means that 10 units of delay is the slowest path through the circuit. Now, after we've actually determined what the critical path of the system is, we can go back to the circuit and determine the criticality, the relative criticality of all the connections in the system. So we might say, OK, well, this path was the slowest path in the system, so we're going to color those red to indicate that they're highly critical. And this output we get in 5 units of delay, that's really only half critical, so let's kind of color those to be blue to just say they're not very critical signals. Okay? Now, unfortunately, the entire static timing analysis process is really computationally intensive. Essentially, we have to walk the entire netlist, and we're going to have to visit each of the links multiple times. Now, what this means is that in the context of simulated annealing, okay, static timing analysis is really too expensive to perform after we make every single little change. So for a large circuit, we might perform, I don't know, hundreds of millions of annealing moves. Now, because of this, classical placement tools like, again, VPR, only run static timing analysis kind of some of the time, very occasionally. Maybe they might make 100 of thousands of moves and then do static timing analysis and then do another 100 of thousands of moves. Now, what this means then is that we'll have really good timing information right after we perform static timing analysis. But we're going to really quickly lose this accuracy. And this can actually lead to some kind of less than ideal results. So let's look at an example of this. So here we have just a really simple circuit. And just for illustration purposes, I've said that the inputs and the outputs of the circuit are fixed. Okay? So basically, we're just trying to find the placement for the logic block A. So OK, we're going to begin with whatever arbitrary placement. And we're going to perform static timing analysis to get the criticality of all the connections. We say, OK, well, this is the critical path. Okay? Then we're going to run the annealing saying, OK, well, this critical path, we should probably make it shorter. OK, so we do. And we say, yeah, I did a really, really good job. I took this highly critical path and I made it really short. Unfortunately, what I didn't realize, because I didn't perform static timing analysis during the annealing, is that I inadvertently added so much kind of cheap delay to a formerly non-critical signal that I made it critical. But, of course, the placer doesn't realize that until I run static timing analysis, I actually update my criticality information. Now, at this point, right, after I've run the static timing analysis, I can say, yes, OK. This is the critical path through my system. Let's make that one short during the following annealing steps. So I say, OK, fine. I'm going to anneal again. And I say, yeah, I did a really great job. I removed all the expensive delay from here. And by the way, I happen to put it back on some other net. Now, obviously, after I perform another static timing analysis, I'm going to realize, hey, I actually have the wrong criticality again. And I'm just going to come back to where I started. Now, basically, what this means is that kind of very slowly, I'm going to oscillate between having this solution and this solution. Right? So this one is particularly attractive when I think this is the critical path, and this one is particularly attractive when I think this is the critical path, or link. Right? Now, of course, what the best solution is to kind of balance the delay between the two inputs, such that neither one is particularly long. Now, that said, because I don't perform static timing analysis very often, I can create a mismatch between the criticalities that we use to calculate the placement cost and the actual values of the criticalities of each of these links. Thus, I'm never going to find this ideal placement. Now, we can actually see this happen exactly in action in a real circuit. So here I show the simulated annealing run of a particular application. Shown in blue, okay, are going to be the results when I've allowed the placer, in this case VPR, right, to perform static timing analysis at its just default rate. Okay? And the other one, shown in pink, I'm going to ask the placer to perform static timing analysis much more often, 1,000 times more often. Now, while this, when I run so much static timing analysis, it's going to be really, really, really slow. But if I just kind of ignore that just for the moment, we can see that we get much more stable results when we update our timing information more often. So the horizontal axis on this graph shows kind of the progress of the annealing from a high temperature to a low temperature, start to finish. And the vertical axis is going to be the normalized critical path delay for the placement at any given point during the annealing process. So what we can see is that when we only update our criticality information, relatively infrequently, in blue, right, we get this very unstable placement. This is particularly problematic given that this instability continues all the way through to the end of the annealing process. Now, largely, this is due to the fact that, of course, the placer doesn't realize when we're actually making the critical path delay of the entire placement worse. However, when we update our timing information really often, as shown in pink, right, the critical path delay improves much more gracefully. We get some oscillation here, but towards the end, okay, it's basically making the system better. Now, of course, this costs us a lot in terms of CPU time. But we'll kind of worry about that a little bit later on. Now, largely, this is because, unfortunately, our concerns surrounding timing-driven placement actually go beyond just computational time when we start talking about registered circuits. So here, okay, we're going to attempt to place a really simple circuit, right? It's just a register. Now, if I use the cost methodology that I've described, okay, really frequent static timing analysis can actually cause some convergence problems within the annealing itself. So consider this, okay? So we have this placement, and we calculate the cost of it, right? We then perform static timing analysis. So we have our criticalities here, and then we make a move, and we say, I did a really good job because I took this link that had a lot of delay on it, and I made it really fast. After that, of course, we're going to perform static timing analysis again, and I'm going to update my criticality information. And basically, I'm just going to kind of oscillate again, just like what happened before. The register is going to kind of ping pong between these two locations. Now, in some sense, though, this is a lot larger of a problem than the oscillation that we had before, because the oscillations are going to come up much more frequently. The more we do static timing analysis, the faster this register is going to want to switch from point A to point B. On top of this, it turns out that we'll never actually find, of course, the ideal balanced location, just like what happened before. Now, given, of course, this kind of register movement, it ends up becoming really a big deal, because, of course, the placement tool is already worried about optimizing wire length and delay, right? So this makes for, quite literally, a moving target, right? And it's really just going to confuse the placer as a whole. And in the end, it can destabilize the placement. And we can actually see this occur when we perform placement on a heavily pipelined version of the exact same netlist that I showed before. So again, in blue, we're going to show the critical path delay of the placement when we perform just the default VPR amount of static timing analysis. And in pink, I'm showing the results of when I do 1,000 times more. So basically, although I might get some kind of critical path delay oscillations, when I don't perform very many timing updates, at least the placement converges to an acceptable solution. Now, clearly, when I try to perform lots of static timing analysis on a heavily pipelined circuit, because, of course, I did this because I thought I was going to improve the accuracy of my criticality information. Well, not only is the tool really, really, really slow, I just plain and simply fail to optimize much of anything. So basically, okay, I've identified two problems within existing techniques to do timing-driven placement. So first, we need some way of updating our timing information in order to keep it accurate. Okay? Unfortunately, well, the thing is that in order for it to be usable during the annealing process itself, it has to be really, really fast. Second, we need a new way of calculating kind of the cost of a move so that we don't leave the door open for oscillation and some of the convergence problems for pipeline circuits. So in order to keep our criticality information up to date efficiently, we actually came up with just a really simple but really effective solution. Now, I don't really have the time to go into the implementation details right now, but essentially, what we do is we take advantage of the fact that we already needed to calculate the change in delay for all the links or all the connections that we moved during the annealing process just to determine the change in the placement cost. So why don't we also use that change in delay to update the criticality? So if we kind of return to the example from before, when we move block A, right, we increase the amount of delay on one of the links and we reduce the amount of delay on another one of the links. We can use this information to kind of recalculate the local criticality of these links. Now granted, this doesn't necessarily provide us with perfect timing information. Okay? We actually need, of course, a real static timing analysis in order to do that. But our approach is really, really fast. And more or less, it helps us keep the timing information that we do have as relevant as possible in between when we can actually afford to do a full static timing analysis. The second improvement that I'd like to make is actually in the way that we calculate cost. So given that we now calculate a new, albeit kind of an approximate criticality after every single move, we can redefine the timing cost such that it's the current delay of whatever link multiplied by the current criticality that we have. So when we use this cost function and we revisit the kind of balancing example that we had from before, we can see that we no longer prefer either of these equally bad placements. Instead, we would rather go towards a much more balanced solution. Now, this is significant because we think it's going to solve our convergence problem. So looking at our results, I mean, I really have way too much data to show all of it here, but I can just kind of summarize it. So I mapped 22 of the largest benchmarks that come with the most popular academic FPGA CAD tool, the VPR tool. So I placed each one of these benchmarks using 3 different approaches. So first, just in blue, the default VPR settings. Okay. Second, VPR, but doing very frequent static timing analysis. So I'm showing that in pink. And lastly, shown in green, is going to be our new technique with the incremental updates and the new cost function that I described. So again, the vertical axis here is going to be the normalized critical path delay. This time it's going to be the geometric mean across all 22 benchmarks. Okay. So along the bottom here, though, I'm going to show 2 different sets of benchmarks. So on the left-hand side, the 22 original benchmarks that came with VPR as is, and on the right side, the same benchmarks, but just heavily pipelined versions of those. So what we can see is that at least for the original non-heavily pipelined circuits, we can really easily beat the value or the results provided by default VPR. We get 10% better critical path delay. Furthermore, we can really handily match the results from VPR with really frequent static timing analysis. Now that said, we should remember that our technique is just orders of magnitude faster than VPR with frequent static timing analysis because we don't perform any more static timing analysis than just the default values. So it's as fast as this tool, but we get the quality results of that tool. Now, looking at the heavily pipelined applications, we can see that our placer does even better. Comparing our approach to the default VPR value results, we see that we get 41% better critical path delay. And compared to the results when we perform lots of static timing analysis, we get 26% better critical path delay. So the kind of really dramatic improvements that this approach is capable of achieving over a lot of different types of applications actually led us to file for a provisional US patent back in mid-December. And right now, actually, I'm in the process of discussing licensing options with a couple of companies such that this can actually be incorporated into commercial FPGA tools. So enough about placement. Kind of shifting gears and getting back to what I was saying earlier. Okay, heavily pipelined applications can actually cause problems for multiple different aspects of the FPGA CAD tools. So now I'd like to talk about some of the issues that come up during routing. So what does a router do? Well, after placement, basically, we know the where and the which, but not the how. Right? So we know where each logic block would like to be. That was the entire job of placement. And we know which because just based upon the application itself, we know which blocks have to be connected to each other. However, we don't know how they should actually be connected. So that is, what exact paths through the interconnect network should we take? So far, I've just kind of assumed that I'm going to be able to connect all the different points that I need to without very much trouble. But that's not necessarily true. So the router's job is to actually determine exactly which interconnect resources that every signal should use. So for example, this signal, which wire segments should it try to occupy? Where should it kind of try to turn? And most importantly, is this connection going to interfere with any of the other connections that I have to make in the entire system? So how do we actually do this? Well, the most common technique for FPGA routing is an algorithm called the Pathfinder negotiated congestion algorithm. Now that's kind of a mouthful, but basically at its heart, Pathfinder uses Dijkstra searches, multiple Dijkstra searches, or kind of wavefront expansion searches to find the cheapest way of connecting any particular signal from source to sink. So let's kind of show just a really brief illustration of what would happen when we try to make the connection between C and F. So our Dijkstra searches are going to begin at the output of C, and gradually we're going to explore all the things that are attached to C. So we get something like this, and we're going to continue expanding our searches until we eventually find the cheapest path that connects the two blocks. We can then route the rest of the signals that we have in the system in turn, also using Dijkstra's algorithm. Now, when we're done, we're we're going to kind of check and see, are any of the wires congested? So that is that we need a single wire to actually carry multiple different signals. Of course, this isn't actually physically feasible because C and D are two independent signals. They can't occupy the same wire. Now, if we do get this kind of congestion, well, then we actually, this is where basically the iterative negotiated congestion part of the Pathfinder algorithm actually comes in. So essentially what we do is we allow different signals to kind of bid on the routing resources that they would like to use. Essentially how this is accomplished is we gradually increase the cost of using a contested resource very slightly, and then we repeat the routing process for another iteration. Now basically our hope is that we can slowly encourage signals that can use other routing resources to do so and leave the most contested resources for those that really, really need them. So this entire process is called congestion resolution. Now that said, okay, just like when we were discussing timing-driven placement, okay, merely providing a feasible routing where all the connections are on their own wires is really only half the battle. Okay? That is, when we get into the situation where we have congestion and we have to resolve it, we really should consider the timing impact of each of the different links. So, okay, well, say for example we have some netlist and we've been given the placement for it. Basically, we'll go ahead and we'll route it. Okay, and after we do this, we might realize, hey, actually, there's some congestion in the system. It turns out that the non-critical link between M and N and the critical link between L and Q actually want to use the same two wire segments. Now this means that during the next routing iteration, we're going to have to push at least one of these signals away from kind of its shortest, fastest, its most preferred path. Okay. The thing is, when we do this, we really have to consider more than just the congestion. We also have to give kind of timing critical signals a little bit more special priority. Now, existing FPGA routing tools actually do this by performing something called timing-driven routing. Now, how this is done is basically we add some terms to the cost function. So basically, we change the cost of a wire depending on what signal we're actually trying to currently route. So specifically, okay, the cost is based on how critical the signal was during the last routing iteration. So connections that were highly critical are going to try to reduce delay as much as possible. And they're going to route largely ignoring congestion. While less critical signals are going to basically try to avoid congestion, even if that means taking a little bit slower of a path. Now thus, when we try to route the connection between M and N again, since during the previous routing iteration, this connection wasn't very critical, the searches during the next iteration are going to try to avoid this congested region as much as possible. This means that the wavefront expansions are kind of going to shy away from this area. And chances are we're going to find a path that looks something like this. Now, the connection between L and Q, on the other hand, was found to be highly critical during the last routing iteration. So the wavefront expansions are going to largely ignore congestion. So instead, we just want to find the fastest path. Right? So this means that the explorations are probably going to include wires that already have signals on them. And eventually, we're hoping that we're going to find a routing for the entire system that looks something like this, where we successfully pushed away less critical signals, allowing critical signals to take the most direct paths. Now, while this is the way that virtually all modern FPGA CAD tools actually perform timing-driven routing, let's kind of take a step back for a moment. Okay? So we learned some things when we tackled timing-driven placement. Can we apply any of the same lessons that we learned from there here? Now, basically, we can kind of see where there might be some problems. Specifically, just like in classical timing-driven placement algorithms, right? We do something, we update the timing information, and then we do something else based on that timing information. So in this case, we route, we update the criticality information, or the timing information, and then we route again based on that timing information. Now, the problem that comes in, then, is who's to say that the criticality of a signal is going to remain the same in between routing iterations? So let's say that we have a particular connection that we need to make, right? So we're just going to connect the X's. And we have some congestion in the system that's indicated by the kind of green blobs there. During our last routing iteration, let's say that we found this link to be critical. Okay? Now this means that during the next routing iteration, we're going to search, largely ignoring congestion. Okay? Thus, when we route, we're going to find some really fast path that might use some of the congested resources. However, if we actually look at this path, we find out, hey, you know, it's actually so fast, it's not timing critical. So we should have paid attention to that congestion. And we say, oh, OK, that's fine. We'll fix it during the next routing iteration. Right? So the next time we route this signal, we say, OK, last time the route was really fast. So don't worry about delay. Let's just try to get rid of some of the congestion in the system. So this means that we'll find a route that looks something like this. Right? In this case, a slow one that avoids all congestion. Now, of course, obviously, this doesn't fix anything because the connection, or because this route is actually really slow, and we'll just end up going around in a circle here. So what exactly is the problem here? Well, just like when we did timing-driven placement, we find that there's a mismatch between the actual criticality of the path and the criticality information that we forward from the last routing iteration that we use to actually search for that path. So basically, we solve this problem by eliminating the need to actually forward any criticality information between any routing iterations. Instead, what we allow is a search to discover the criticality of a net for itself. Now, how we do this is we actually launch multiple simultaneous searches that each assume that the connection is going to be a different criticality. This is a technique that we call the assumed criticality routing approach. So if we launch n searches, okay, where each is going to have a criticality, we're each going to assume that each is going to have a criticality between 1 over n and 1.0. So in the example I show here, right, I've launched 3 assumed criticality searches, and each is going to have a different criticality of 1/3, 2/3, and 1.0. Now these searches are going to spread in completely different ways, right? That is that the lowest criticality searches are going to try and avoid congestion, and the highest criticality searches are just going to try and travel along the fastest wires. So eventually, okay, one of the searches is going to reach the destination. Now, just as it's about to explore the destination and complete the routing, okay, we can determine the real criticality of the path that we actually found. So in our example here, right, our assumed 1.0 criticality search actually encountered the destination. At this point, we can recalculate the cost of the route based upon the actual criticality instead of just the assumed one. So in this case, it seems as though the path we found between the source and sink was actually quite a bit faster than what we initially assumed. So we made the exploration based upon the assumption that this net was going to be 100% critical. Thus, we should disregard any of the congestion that we end up hitting along the way. However, it turns out that the route we actually found was so fast that it was only 40% critical. And because of this, we should have been paying for all the congestion along the way. So the real cost of the path is a lot higher than what we were originally assuming. Now, that said, we figured this out, right? So we can correct the error, and we can push this search back into the exploration queue with the real cost of the path we actually found. Now, of course, since this path cost is, it's going to be really high, right? So it's going to be a long time before we actually see it again coming out of the other end of the priority queue. Anyways, the searches are going to continue. And eventually, one of the other explorations is going to find, again, another path up to, but not including the sink. Now this time, our assumed criticality is actually much, much closer to the actual one. Now we explored under the assumption that this link was going to be 67% critical, and the route that we actually found was 60% critical. Now what this means is basically we've already correctly calculated kind of the delay versus congestion cost for this route. Now this is actually our hope, right, that the discrepancy between the real criticality of a route and the criticality that we use for exploration is going to be small enough that it doesn't really make much of a difference. Now that said, we can correct whatever small error there is, and again, we're going to push the search into the exploration queue with the real cost of the path. Now, of course, since we already basically correctly calculated the cost, it's not going to go very far back into the exploration queue. The real cost of the path is relatively low. This means that at some point really soon, the path is going to come out from the routing queue, and we're going to complete the route to the destination. Now, basically, since this was the cheapest way that we found, it's likely the best path to connect these two points under the prevailing conditions of whatever congestion and delay we have in the system. Now, while I don't really have enough time to talk about the details here, again, similar to what happened when we were discussing the timing-driven placement, some additional problems can come up when we consider routing for pipelined applications on some architectures. Now, I can kind of really quickly summarize things. So in essence, okay, pipelined applications pose a unique problem. It's a problem actually called the end delay routing problem. Now, basically, in every respect, the end delay routing problem is even harder than regular routing. Okay, basically, we still have to worry about all the same congestion concerns, plus there are more things even on top of that. There are actually two algorithms that try to address the end delay routing problem. Most recently, a tool called QuickRoute. Okay. Now, the thing is that both of these approaches are only timing-driven routers. They're not, they're both congestion-driven routers. They're not timing-driven routers. So why weren't there any timing-driven solutions? Well, basically, because conventional ways of making routers timing-driven cause these routers to kind of oscillate wildly and produce poor results. Now that said, since my assumed criticality routing approach largely solves the stability problems, we were able to build what, at least is to the best of my knowledge, the first timing-driven end delay router. So some of those results are actually what I'm going to show here. So again, unfortunately, I have way too much data to show all of it, but I can kind of give you a small snippet or summary. So in this experiment, okay, I placed 9 pipelined applications and then routed the netlist using one of two approaches. So first, shown here in blue, the original QuickRoute algorithm. And second, shown in green, the QuickRoute algorithm, but replacing the regular searches with our assumed criticality approach. So again, the vertical axis on this graph is going to be the normalized critical path delay, and then we're going to take the geometric mean across all 9 benchmarks. Along the horizontal axis, it's a little bit different. What we see here is the results for the 2 routing approaches across 3 different architectures that I was looking at in this particular study. And actually, I'll be talking about what kinds of things go into different FPGA architectures in just a moment. Anyways, what we can see is that basically across the board, my assumed criticality routing approach does really, really well. So it consistently produces better critical path delay, 38% better on average. Now, again, kind of stepping back for a moment. Yeah?
In both cases, you showed critical path delay only as a measure of goodness. Mm-hmm. What about resource and area consumption?
Right. So actually, I also have some track count numbers. It kind of made the graph too complicated, so that's why I didn't include them. But on all 3 of these, actually, the wire cost is exactly the same. I mean, it's plus minus just a couple of percent. Yes, absolutely. Basically, the wire cost ends up actually even getting better. So my timing-driven placer produces better wire length and better timing. So. But yeah, again, on the 2 graphs guy, there's too many colors. There's only so many colors you can you can put in Excel and people can actually tell what you're trying to say. So, kind of switching gears again. While messing around with CAD tools is fun and all, and whatever the improvements that I got were really nice. Ultimately, okay, applications run on some piece of silicon. Now this means that the inherent efficiencies of whatever underlying FPGA that we're mapping to really plays a major role in determining just the overall potential of the system. Because of this, in just the last couple of minutes of my talk here, I'm going to be talking about what I'm working on right now. The last phase of my dissertation work, which is FPGA architectures. So I said before that heavily pipelined applications can end up putting a really large burden on FPGA architectures. And now largely, this is because deeply pipelined circuits can have so many registers in them that they can just simply overwhelm the resources that commercial devices provide. Now, it wouldn't be unheard of to say that a heavily pipelined application uses 75, 85% of the logic blocks simply for the registers and not for their logic. Now, this kind of inefficiency kind of stems from the general philosophy that FPGA architectures have been built from in the past. So commercial FPGAs typically provide logic blocks that consist of one computational element and one register, one optional register. Now this kind of setup makes a lot of sense for what we generally consider to be a fully pipelined application, or a circuit where basically you have a register after every operation, one register after every operation. Now, however, in order to get the absolute fastest circuits that we can, and this is actually something that Turner and I were talking about a few days ago, we often need to super pipeline the system. So, for example, okay, if we would like to go from one logic block to another in a system that's being run at a really, really high clock frequency, we may not be able to travel more than, say, a distance of one logic block before we have to enter a register. Now, thus, this signal can end up looking something like that. Now, this then, in turn, ends up creating a netlist that looks something like this. Instead of just one register after each operation, we have multiple registers before and after each operation. Now, of course, trying to map these kinds of circuits when we have a basic building block that looks like this, well, it can be a problem. Now, on top of this problem is only going to really get worse as fabrication technologies scale to smaller and smaller feature sizes. Now, the reason for this is because the delay required by the logic is going to become less and less significant. As feature sizes get smaller, what's going to become more significant is the delay incurred in the interconnect. Now, this means that at some point, we don't have to worry about pipelining the logic in the system. We have to worry about pipelining the interconnect, just the wires. Now, this is why I'm currently looking at different architectures that can increase the available density of registers in the system. So I can start with just the classic logic block, something that we know works for conventional applications, and then start adding things to it. Now, of course, the big question is, there's a lot of different ways to add registers to the system. So what's the most effective and efficient way? So one thing, for example, if I include multiple registers inside one logic block, what are the area implications? In addition, for example, here I've added more outputs to the logic block. So if I have more inputs and outputs, what happens to the capacitance of the wires in the interconnect? Let's see, something else. Okay, so last couple of generations of Xilinx devices have added the capability of turning some of their computational units into variable length shifters. What happens if we include these? Or better yet, what happens if we modify them to be able to register multiple signals? Now, are these the types of resources that our heavily pipelined applications can really make good use of? How about putting registers in the interconnect? Okay, so we said that the wires are probably going to be the slowest part in the system. So why not try and embed registers right inside the communication network itself. Now, all of these things, and a couple more actually, are the architectural modifications that I'm looking into. So I think I'm more or less out of time. So to sum things up, okay, reconfigurable computing platforms are really, really great for just a wide variety of reasons. We talked about some of them. However, looking into the future, okay, they need to have better support for heavily pipelined applications. Now, part of the solution is just better CAD tools. Basically, the CAD tools need to be aware of the needs of heavily pipelined applications and some of the pitfalls that can actually trap traditional approaches. Now, I presented a timing-driven placement tool and a timing-driven router that drastically improves performance over existing approaches. In general, we got a 40% improvement in critical path delay by using my techniques. Now, that said, we also need to start looking at the FPGAs themselves. So over the next month or two, I hope to have some answers on how we can effectively increase the overall availability of registering resources in the system. So with that, I conclude my talk. Thank you.
Well, we have another half hour, actually.
Oh, all right. They told me I planned for a 50-minute talk.
Or backup slides or whatever.
Well.
Questions?
I'll ask a couple of questions about what you've already talked about anyway.
Uh-huh.
One, how does the runtime of your tool compare to VPR?
Okay, so hang on, actually, let's see if I can go to some of this. So for, why doesn't that work here? Can I do that? Ah, okay. So for the placer, the runtime actually, and I talked a little bit about this, but the runtime actually for both of these is very comparable to just the default VPR runs. So when you look at the updates that I have to do, when you look at the updates that you have to do, basically per link, the extra computation that you have to do is like, I think it's 2 adds and 1 divide. That's it. As compared to doing static timing analysis, which is, order however many nodes you have in your net list. I mean, it's just way, 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 way faster.
And the other thing is, have you looked into making this parallel?
Well, okay. So I will say, so the placer doesn't have any issues with runtime. However, let's see. Can I go back to this? Is this going to work? I don't know how to do this. Hang on. Aha, okay. This, the router does have some issues with runtime. And basically what it is for every search that I do, instead of doing 1 search, in this case I do 3 searches. Right? So I have 3 times as much work to do, at least in some sense. This tool does end up having a runtime issue. Right now, I end up having to run more than 3 searches. I think the number that I get, that I can run, the number of searches that I can do without really affecting the quality of the results I get, is about 5 to 6. So basically, my runtime is about 5 or 6 times slower. But all these searches are totally independent of one another. Basically, I just say when anybody's reached a particular destination, everybody else has to know. But all the explorations themselves, they're just regular Dijkstra searches. So basically, if I take any, say I have some routing resource sitting here, it can be visited 3 times. So normally it can only be visited once. That's how Dijkstra works, right? Any of them can be visited 3 times by the 3 different searches. By any one search, it can only be visited once. But all 3 of the searches are done completely independent of one another. So that would be something that's really easy to parallelize.
When you say the runtime's not really significant for the placer, do you mean that the runtime is comparable to VPR, or it happens in a microsecond? The
runtime is, so to say specifics about the runtime is actually tough because my tool isn't actually in VPR. My tool is in this totally different form. So saying that the runtime of one tool versus the runtime of another it's very difficult to fairly compare them.
I'm just looking
In terms of
for
the
seconds
complexity,
versus minutes.
right. So I would say that, well, okay, if you're going to do 3 extra operations per move or per link, I mean, it's going to be small percentages. I would be shocked if it said that it increased my runtime by 1%.
Yeah. But yeah, so it's an increased runtime. So VPR still has this kind of standard runtime.
Yeah.
And your optimizations will help it find a better result in roughly the same amount of time.
Well, so I'm going to find better results in just a little bit more time. So what I can do is, if I really wanted to scale it back and say, okay, I'm going to run exactly the same runtime, chances are I'm still going to get better results. I mean, when you're talking about 41% better critical path delay, if that becomes 35% better critical path delay, you're still basically getting it for free.
Yeah, it's okay.
Follow-up, memory consumption?
So memory consumption for the placer, there's no effect at all. You still have to store all the same things that you had to do before. You're just updating them more often. This tool actually does, the timing-driven router does have a memory problem. But that isn't actually largely because of the assumed criticality part of the router. It actually has to do with the fact that let's see. Sorry. Okay. Slide 50. That has to do with the fact that Quick Route actually has a memory problem. So the end delay routing problem is it's different, and you actually can't use Dijkstra's because so what the end delay routing problem is: connect point A to point B going through exactly n registers. So that exactly through n registers totally blows away the Dijkstra search. You have to replace it with something, and so the Quick Route algorithm actually does that. The Quick Route algorithm, unfortunately, has some memory issues. My tool is actually implemented on an old version of Quick Route. The newest versions of Quick Route actually have a very efficient way of keeping track of the routing, the progress of the router. So the memory footprint is a lot lower. But a lot of so for example, when I did this testing, and I got these results, actually, the router takes a really long time, largely because of the fact that it has this huge memory footprint that doesn't have to be there. But I started implementing this way before those guys had come out with this new way of tracking information. So.
And what are we talking about, roughly? Factor of 10?
Well, so in this case, I would say that just by adding in the assumed criticality portion, just that part, you get a n-way increase in the memory utilization. So if n is 3, 3 times more memory. And largely it has to do with the nodes in the graph have to know, right now I'm being visited by this search. Oh, now I'm being visited by that search. And it has to be able to keep them separate. So that while it makes it very parallel, it also increases the memory utilization.
So the amount of information, memory that stays, shared between the searches and immutable.
Oh, the amount of information that's shared between the searches is 0, almost 0. So again, that's part of the reason why it makes it super parallel. It's kind of these embarrassingly parallel kind of problems.
Another quick question. How does the type of the interconnect between the logic blocks or the density of them affect? Because I know that the FPGA, like the Vertex and all of them, had different types of interconnect between the cells. I have direct connections, hex connections, octo and long lines.
Right.
So how would that be incorporated into this? Like if you wanted to minimize the long lines, does it may have higher capacity, more delay than maybe a direct?
So in terms of the router or in terms of the placer? So basically, actually, both the placer and the router kind of they capture the fact that you have this heterogeneous routing structure. what the placer does, okay, is when it says, okay, I have some block that needs to talk to some other block, before I even run the placer at all, I figure out the quickest way of connecting these 2 points. So generally that would be going on the long lines, right? And what the hope is if that ends up actually being the critical path in your system, that the router later on is going to say, oh yeah, this is a really long path, that should probably go along the long lines. So it basically, it tries to take that into account. That's not necessarily going to be true, because if I make all the connections in my placement critical, not all of them are going to be able to go on the fastest lines, right? So there is this kind of mismatch, but basically they try to say there's a high probability. So the router actually takes the timing into account directly. So basically the delay in the congestion mixture for any given link is going to actually take care of that. And so the Pathfinder algorithm works really, really well on these heterogeneous routing architectures, because that is actually part of the cost function. The only thing is that where you start doing this sort of ping pong business is still going to happen, and so this approach is kind of attacking a different problem.
Yeah.
But yeah.
Well, is the difference between these lines only taken into account in the actual delay in these specific types of interconnects, or would you consider maybe adding some kind of artificial constant to these different types of interconnects to say I want to use more direct lines than long lines?
Well, so the routing is actually performed on the real routing graph. So it knows, oh, there's between point A and point B, I have 6 short wires, direct connection wires. I have 4 hex lines, and I have 2 long lines. Right. Like you actually do it on the real graph. So yeah, absolutely, they take it into account.
Right. My only other question is, aside from just pipelining and having to take care of registers, sometimes in a large system you have wires that have a specific relationship to each other, like they're part of a bus, or they all have similar timing characteristics that are required to make the system work. I mean, I don't see a whole CAD tool that can take the relationship between signals into account when trying to route them. So have you thought of that at all?
So that's absolutely true. And for that matter, actually, so a lot of the signals are these kinds of buses. But because the architectures themselves aren't really bus-based, well, each wire kind of has to fend for itself, just like every logic block has to fend for itself. So basically, they don't use these kind of bus-based techniques because the architecture is not bus-based. Now, when you switch the architecture and then you make the architecture a bus-switched network, then yeah, absolutely. So the routers for those types of systems do switch entire buses, but they don't right now. Or if you go to ISC, Xilinx tools, or whatever, they don't do that because their architectures don't. That's not a reflection of their architectures, basically.
Would that be something that you see more or less going forward?
More, absolutely. More.
Because?
So, in some sense, these kind of bit-wise switching, it's really inefficient. Why? Because FPGAs, at least, or really any of these devices, are constrained by the amount of memory resources that you can put down. So it consumes memory, or it consumes area when you talk about this piece of silicon. Wires are relatively free because you route over stuff, right? But the physical silicon, there's only so much area. Anytime you put down a switch, you have to put a memory, you have to put a bit of memory on that switch to say, oh, well, turn it on or turn it off. So if I have this bitwise switching, well, then I need one memory bit for every wire. But if I do a bus-based, then I can put one bit for an entire bus width. And so you can make the system as a whole much more efficient. However, right now, Xilinx devices don't use the bus-based systems because you get a problem with utilization, right? Buses only make sense when you have 8 bits of information they have to get from here to there. But if you have one that goes here and one that goes there, then you end up basically making a fragmentation issue.
I could make the argument then if we are in fact bringing more software applications, or applications that were built for processor originally, then we would see more of that.
Absolutely, absolutely. And so that's when you get like an AMBRIC, right? You get that type of. I think they have like 32-bit buses that they switch around, and so that's their like kind of atomic unit because the underlying computation fabric is built that way.
Well, I guess a heterogeneous structure where you do have some bit-wise interconnect and some bus-wise interconnect would probably make more sense, like using more bus-like interconnects for a longer transition, go from one side of the chip to the other side of the chip, and use more bus-like structures, and then using more bit-like structures at closer end.
Yeah, absolutely. I think right now, so again, a lot of it has to do with just there's a whole bunch of legacy in FPGA architectures right now, and so since the logic blocks are built a certain way, they need to get this capability of having like 100% utilization of the wires, basically, and that's why they have everybody kind of has to be able to be going independent directions. And so that's the reason why they don't really incorporate many of these buses, because frankly, a lot of it's even just the CAD tools. Their CAD tools historically have never been able to handle it because they've never taken that into account. So you kind of get this chicken and egg problem where, well, we can't put it in the system because we don't know how to make the CAD tools work with it. Well, we can't make our CAD tools work with it because we've never built an architecture that needs it.
And then you end up with the spaghetti wires all over the place.
Right. Yeah.
Right. Other questions?
I missed the first part, so I have to apologize. But I'll go over it with you when we get together. Actually, if I had a copy of your slides, it might help. So,
Yeah, I can.
you know.
I guess I have a slide deck, but I don't know how I could get them to you.
Yeah, if you email them, it would probably work better.
Okay.
So.
Maybe I can give them on
Yeah,
a
if you
key
have a USB,
to
yeah,
Alexandra.
that'd be great. Yeah, I
Maybe
have
you
one.
can-
I have it.
Yeah, if you have a USB key.
I don't have it with me.
Oh,
but I
okay,
can get it
okay.
upstairs.
Okay. Okay.